I need to do the same thing here. And so maybe to make it clear, I will put an AL under the mass for aluminum and a PB under here because this is the mass of the lead. And likewise, this is the AL for, this is the specific heat for aluminum, so I'll put an AL, and this is the specific heat of the lead. So again, let me put a PB under there. And then likewise here, this is the change in the temperature of the aluminum, and this is the change in the temperature of a lead. And again, if you're not careful, you'll see there that it just says change in temperature, and you'll think, oh, change in temperature, well, they're the same. They're both some number, but no, these are two different materials. And so what the change of one may not be the same as the change in the other. And of course, let me not forget the absolute value here. So, okay, wait a minute. This is the absolute value, and this is the absolute value. Because again, I'll say it, that it would be a mistake if I didn't have the absolute value, because I would go final minus initial, and the one that cools down, which would be the aluminum, would turn out to be a negative number. There's just no way you could say a negative number is equal to a positive number. And that's not what we meant when we said conservation of energy. We meant that energy leaving, so the absolute value, is equal to the energy going into the lead. All right. So I'll keep going. But now I've shown you the kind of the two big things that really throw students off on this calculation. The absolute value and the mixing of, hey, there is two different masses. There is two different specific heats. There's two different changes in temperature, because there's two different materials. And I guess that would have been a harder problem, might have three materials. And maybe two lose and one gains. And so we'd have two on this side and one on that side. But again, then we would have to say they're the absolute values. The two losing, the absolute value of those would have to equal to the one gaining. And then of course we would have three masses and three specific heats and three changes in temperature. That'd be a little harder problem, but not unreasonable to do. And so you'll come across those. All right, so now I can actually do the calculation. So the mass of the aluminum was given. So here we got the 90 grams. Then we've got the specific heat of the aluminum. And if you remember that chart I was just showing you, it was 0.215 calories per gram per each degree Celsius. The change in temperature of the aluminum, well, that's where kind of the unknown comes in, right? I don't really know what the change in temperature is. I do know that it starts at 50 and it's going to cool down. And so maybe I will write this as final temperature minus 50. And so that's this piece of the puzzle here, this calculation. What is the change in the temperature? And so I don't know what that is. But part of that change is the final temperature. And that's the ultimate question here. What will be the final temperature when you take these two objects, one at 50 and one at 20, and merge them together or touch them together? Now, let me not forget that this needs an absolute value in it. And in fact, before I do the other side of this equation, you'll see the effect of this absolute value. Here's the 90 grams. Here's the 0.215 calories per gram per each degree. And of course, absolute value says the following. It says if it's already a positive number, don't do anything to it. If it's a negative number, change it. So in other words, if it's negative 3, change it to a positive 3. And so that's why this one I'll leave alone. It's positive. This one's positive, leave it alone. But this one I know is going to be negative. It's going to cool down. So I need to change it. And the best way to write it is then write it as 50 minus final temperature. And that way I'm done with my absolute value symbols in my mathematics. Okay? And so I'll say it again because this is what I've kind of discovered in the past that it's this absolute value. It's the math here that has given students the hardest time in this calculation. And I just got to keep emphasizing it's absolute value when you said this statement right here. And of course, to actually then do a calculation with absolute value, I got to look at it, and if it's positive, leave it alone, but if it's negative, I got to switch it, and that's what I'm doing. This one's negative, so I switch it. But these other ones are positive. Now, the same thing on the other side here. This would then be the heat going into this lead piece. Okay, so the mass is the 300 grams. The specific heat of lead, I didn't look at that one on the table. Let me look at the book. I'm not even sure it was listed in the book. Bummer. It is not. But I'm pretty sure it's very, very close to the gold there. And so let me put the 0.031 calories per gram per each degree. And while I'm talking, I'll let Ron here look it up there. We can find it. Then the change in temperature, and again, I don't know the change in temperature exactly of lead.
0.128.
0.12, what units?
Oh, wait a second. I gave it joules for, sorry. There it is.
He said 0.128, but
No, that's the wrong units.
but I think that's joules.
0.0305.
Yeah.
That is calories.
Yeah. Okay, good.
That's it.
Yeah. All right. So good. So he's confirming that it is that number. Okay, thank you. Oh, and then, of course, this change in temperature would be the final temperature minus the 20. Now, again, let me say this mathematics means the absolute value of it. And so let's talk about the math of absolute values again. But notice I did something here that, if it wasn't obvious, let me point it out. I'm going to put them together and hold them together, and eventually they're going to get the same temperature. So this over here, the final temperature of the aluminum, is the same as this one over here. So I have one equation with one unknown. I don't have a final temperature. I guess I'm trying to say is I don't have two final temperatures. There's only one final temperature. They come together until they reach equilibrium. I have two different initial temperatures, right? I have the initial temperature of the aluminum and I have the initial temperature of lead. But the real key to this problem is to realize there is only one final temperature. So I have two different masses, I have two different specific heats, I have two different changes in temperature, I have two different initial temperatures, but I only have one final temperature. Now, when I do the absolute value, this is a 300. This is a 0.031 calories per gram per each degree. And since the lead is warming up, this would be a positive number. So again, when you do absolute value, don't change anything. So I won't. So this would just be final minus the 20. And so that's how the math works out. So now let's grab the calculator and actually work this math out so we can find out, this answer. What would be the final temperature when I put this lead and aluminum together? And maybe I'll just do this first. And so 90 times 0.215 is 19.35. And if I watch my units here, this would be calories, and then grams would cancel off, and I would have per degree Celsius. This then would still be the 50 minus the final temperature. This one here, 300 times 0.031 would come out to be 9.3. And then, of course, the units would be calories per degree Celsius. And then this would still be final temperature minus 20. And then the units on each side that I've written would cancel off. And I didn't put degrees Celsius here. Maybe I should have. And so that's going to be the unit for the final answer for the final temperature. It's going to be in degrees Celsius. And so I'll just do one more step before I do the distributive property. Over here I have the 19.35. And if I divide that by the 9.3, I get 2.08. And it looks like I ran out of room there on my whiteboard, so let me continue the calculation over here. Maybe I'll just keep going and get this erased for later on. But if I now do what in math you call the distributive property, the 2.08 multiplied by the 50 is 104.0 minus the 208 times the final temperature. Let me just double check that. Look over here. Yeah, 208 times 50 and then 208 times final temperature. And the other side of the equation is just the final temperature minus 20. And so there's quite a bit of math here, if you will, with the absolute values and the distributive property. And of course now I can move this over to here. So when I add 20 to this, this becomes 124. And when I bring this over to here, this comes 308 for the final temperature. And then my last calculation here is 124 divided by 3.08, coming up to a final temperature of 40.3 degrees Celsius. And so that's the calculation. That's really what I wanted to show you, because as I said, the absolute value, the distributive property, and particularly, changing the change in temperature to final minus initial is kind of an important step to see. And a lot of your calculations on the homework and then of course on the test on Monday are kind of like this. This is how you do a calculation involving the energy and the change in temperature. And I want to point out something very important. Because without this discussion of conservation of energy, the common mistake that students and just a common layperson like to do is just to say, well, you put a 50 degrees together with a 20 degrees, they're going to meet in the middle, right? Well, no, it didn't meet in the middle. The middle would be 35 degrees, right? They differ by 30, and halfway up would be 15, so that'd be 35, and the 15 down would be 35. So if it met in the middle, you would get 35 degrees, and that is not what you get. You do not get. It's not that they have the same change in temperature. They have the same energy. That's important, because the energy is the key to the problem. That's the principle, conservation of energy. There is nothing that says, oh, the change of temperature of one has to equal the change in temperature of another. No, that's not true. You wouldn't expect to take a big ocean that's kind of cold and put a drop of boiling water in it and it meet halfway. It's just such a small amount of water. The energy's the issue, not the temperature. So you got to go through all this math, and then the energies are equal, but the reason the change in temperatures are not equal is because you have other factors involved. And that's actually one of the questions on today's lab, is to emphasize, hey, don't confuse the change in temperature with the change in the energy. Well, the change in energy is the same. One loses, the other one gains. But the change in temperature is not. What we're seeing here is the aluminum is cooling down about 10 degrees. And we're seeing the lead warm up about 20 degrees. And so to decide how the change in temperature is split, it's matter of what are the specific heats of them and how much mass do you have. And this one would be hard to predict because I can see right away that the aluminum has a higher specific heat. So that would tell me right away that I would think that the aluminum would have a smaller change in temperature. It takes more energy to change 1 gram, 1 degree of aluminum than it does for lead. And because of that, I would expect then it to be harder to change the aluminum. And therefore, the aluminum should have a smaller change in temperature. However, I also see that I've got more lead than aluminum, about 3 times more lead. And so it's harder to change something, its temperature, when you have a lot of it. And so that would tell me it's harder to change the temperature of the lead. And so it's the combination of the two. And the combination of the two is in this calculation right here. And you can see that this number here is about twice as big as that one. So by the time we put together the mass and the specific heat, this is telling us the overall ease or difficult of changing its temperature. And you can see that is about twice this one. And so as I sit here and I do the math, and I do more than do the math, I kind of say, what does it mean? I read the math is what I like to say. What do these numbers mean here? I begin to see here that these two numbers together, being twice as big as these two numbers together, telling me it's about twice as hard or takes twice as much energy to change 1 degree of this aluminum block than it does the lead block. And that's why ultimately, when the final temperature is reached, this one will change by 20 degrees, and this one will only decrease by 2 degrees. And so I hope in this long conversation, you're not only seeing how to do the calculation, but you're also seeing how to dig deeper and read the math. Get inside of it and say, okay, what's going on? What do these numbers actually mean here? And of course, maybe the most important thing is just, hey, don't assume that when you put them together, the temperature's right in the middle. That is not at all what's going to happen. Different materials take a different amount. And again, that's why we call it the specific heat. Well, I better keep going because there's a lot of other neat little things here. But they're kind of along this line here. Maybe I should start with water here. What if I did something like this? What if I took a chunk of ice, and maybe to make my math a little bit easier, let's say I just have 1 gram of ice. Now, in reality, so I can show it to you, let me take more than 1 gram of ice, because 1 gram of ice is not much. So I'm going to come over here and grab this beaker now and finally actually fill it up. I've been talking about it. And I have a bunch of ice in this little ice chest here. And so let me kind of load it up. I'll fill the beaker all the way up. Although it's not packed real hard. So this beaker I think is a 600 milliliter beaker. Where is it? Yeah, it's 600 milliliters. But I'm sure I don't really have 600 milliliters, which would be 600 grams of ice, because there's, like I said, a lot of empty space between these ice pieces. I guess I'll be able to tell better once it melts and fills in all those spaces. But imagine this then, as for now I'll just say it's 1 gram of ice. And I take this 1 gram of ice and I take it right out of the freezer. Now, I know this has been out of the freezer for maybe an hour or two. We grabbed it earlier on. But our ice machine up there is set at roughly negative 20 degrees Celsius. Okay? And so this ice, and I'll just say, is starting at negative 20 degrees Celsius. Like I said, it's probably warmed up a little bit from that. But I want to really warm it up. So what I want to do is take my little Bunsen burner here, or I guess this is a Fisher burner, make a little flame, and put that beaker filled with ice in that flame. Now I'll hold off on for a second before I actually do it. Because if I make a plot and I put temperature on the vertical axis and on the horizontal axis I put the energy that I add to it, and I'll just say time, because what I'm going to do is just put it under the flame, and that little burner is going to be adding a certain amount of energy. I don't know exactly what the number is, but every second it's adding the same amount of energy. And so as time goes along, the energy is getting more and more and more and more. And so it'll look something like this. And so here's my beaker. Maybe I'll turn the markers towards you. They're probably hard to see. I can barely see them. But once it melts, they're a little easier to read. And so, let's see, I don't want to get it too hot too quickly. I wonder if I need to lift it up a little bit. Maybe I will. Let me go a little bit. I don't break it. Let me go a little bit higher here first before I get it started. Yeah, it looks pretty good. All right, so I don't want to add energy too quickly. So give it a little bit of space and start heating it up. And let's talk about what happens here in the next 10, 15 minutes. And so on this chart, I guess I would say that it is starting right here at negative 20 degrees Celsius. And of course it's ice, so it's a solid. And so as I'm adding energy to it, and so as we go along the x-axis, its temperature goes up. And so it goes up, 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 up. And something a little different is going to happen at 0 degrees. And that's what I want to talk about. But before I get to 0 degrees, let me just remind you of the structure of matter here, right? This is the mental picture I wanted you to have of a solid. So here's the solid. And when it comes out of the freezer, the H2O molecules are hooked together. And so in my mind, and hopefully in your mind, here's what I see for those ice pieces. They're doing this. They're jiggling like this. But they're hooked together, right? If I toss them in the air, they keep their same shape. If I come over here and grab a piece of ice and toss it in the air, it keeps its shape. They're solids. But as I give them energy, they start to jiggle more and more and more. And as they warm up, if I were to ask myself, how much energy do I give it in order to warm up, I would say, okay, well, let's take how much mass you have. And I'm not yet sure how much mass I actually have. Until it melts really well, I won't know. I'm going to make a guess at 400, okay? And so let me come over here and say I have probably somewhere in the neighborhood of 400 grams. And how much energy does it take to warm up 1 gram, 1 degree Celsius? And be careful here, because it is not one. That's the liquid water. I don't know if you look closely on that chart, but under the solids, they list ice. See, ice is connected a little bit different. Do you remember the difference between a solid and a liquid? Oh, let me come back and remind you. Here's this model of this liquid. Remember, the liquid is what I call kind of a semi-breaking of the bonds. And so on an atomic level, if these are the H2O molecules shaking around, they flow around each other, right? Water is a fluid, it flows. But the ice is a solid, and they're hooked together a little differently. And because they are hooked together a little differently, it could take a different type and a different amount of energy, I shouldn't say type as much as amount, of energy to warm up 1 gram, 1 degree. And sure enough, it does. The bonds are different. So that's why I'm trying to say be careful here. And I need to realize this is ice. And so maybe I should have, said, hey, this is the solid, and it is only a half a calorie per gram per each degree to warm it up. And of course, if I'm talking about how much energy would it take to warm it all the way up to this place where it begins to melt, and in my real experiment, you can see I've already passed that. It's already melting, but not even getting to the point of it melting, I would have to increase its temperature by 20 degrees Celsius. All right, so 1/2 times 20 is 10. 10 times 400 is 4,000. Grams cancel with grams. Degrees Celsius cancels with degrees Celsius. And I would say right here it would take me 4,000 calories of energy just to warm it up. Now, like I said, we're way past that, and so I'll talk a little bit faster here. But in my experiment, it's already melted probably 2/3 of it. And this is just the energy to bring it to that melting point. But here's really this main point. Something very interesting happens right now as the gets to the melting point. Let me take you back where I showed you. Do you remember the difference between the solid and the liquid? Remember me shaking this thing and eventually we get to a high enough temperature where it melts? There it goes. Oh, well, started to melt. See? The bonds begin to break off. The bonds begin to break off. But when you get to the melting point of your material, now of course I'm talking about H2O, but I want to emphasize this would be true for aluminum. This would be true for any material. When you get to that melting point and you start to add energy, the energy you add is breaking the bonds. It doesn't make the molecules move any faster. Now remember, temperature is the speed of those molecules. And this really confused the early scientists because they noticed as they continued to add energy to their water or their aluminum or their lead, and they got to the melting temperature of it. It began to melt, but its temperature didn't go up. And that's what I'm trying to show you in this graph. This graph is saying that once I got it up to its melting point, what would happen is it would start melting all the ice. And in my experiment, we just got there. We've actually just melted all of the ice, and we're past this point of melting the ice. But this part right here is an energy that breaks the bonds. It doesn't make its temperature go up. In fact, it was very confusing to the early scientists, so they called it a latent heat. And latent is Latin for hidden. Because they knew they were adding energy, but it confused them. Because how in the world could we be adding energy? That energy's got to go somewhere, but its temperature is not going up. Now, hopefully it won't confuse you, because I'm trying to tell you that what they didn't know, and what you hopefully are learning here, is that during this step, the energy I'm adding breaks the bonds. It does not make the molecules go any faster. And I'll say it again, temperature is related to the kinetic energy of these. And so if your energy goes to breaking the bonds, but it doesn't go to making them travel any faster, the temperature won't go up. Remember, the principle is conservation of energy. It is not conservation of kinetic energy. They don't have to go any faster. Just because you gave them energy doesn't mean they go faster. It doesn't mean that energy goes to kinetic energy. It goes to breaking the bonds. So we're going to call that a hidden heat, a latent heat. And it turns out that it takes 80 calories to break the bonds of 1 gram of ice. And so we like to say that the latent heat, and of course since we're melting it, we call this the latent heat of melting. I will point out that if you were cooling the water down, you've got to take this energy out and you've got to make the ice. So we also call it the latent heat of fusion. And so the latent heat of melting or the latent heat of fusion is really the same thing. It's just a matter of, are you melting it or are you fusing it together, making a solid. And so if I come over here and I do a calculation then, and I ask this question, Q, how much energy does it take to break the bonds? And hopefully you see it here in the explanation. Well, since it takes 80 calories for each gram to break the bonds, you would have to take the 80 number and then multiply by how many grams you have, which in my case is roughly 400. Actually, by the way, now that it's all melted, you could probably come over here and see. Yeah, my guess was pretty good. It was just a little under 400. All right, so I'll continue with my 400. But this then would look like this. It would say take the mass and multiply it by this latent heat. And in this case, the latent heat of fusion or the latent heat of melting. All right. Let's give you some symbols here. The traditional symbols, of course, is the M. And for the latent heat, we're going to use L. And if it's latent heat of fusion or / melting, we'll do the sub F. And so they just choose the F over the M, but there is the latent heat of fusion. So in my case, and my experiment is actually past it, but if I were to ask this question, how much energy did it take to actually break all those bonds, I would have to say it is 400 grams times 80 calories for each gram. And 400 times 80, let's see, 8 times 4 is 32, and then I have 3 zeros. So it would be 32,000 calories in order to break those bonds. Oh, is this in the way? This here? All right. I'll put that down till we need it. All right, so it's 32,000 calories. And again, I'm well past that. In fact, you can kind of see I'm really getting to almost to the boiling. It's starting to boil. But I want to emphasize then that during this time, the temperature was still at 0 degrees. Now, once all the bonds are broken, well, then of course we're back to, I think, the obvious. We're just back to something that looks like this, a liquid. And as we add energy to it, it makes the atoms jiggle faster, 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 faster. And so we just keep adding energy. And eventually we get to that magical point, right, where they break free. They actually fly off. And now they become a gas. And in my little experiment, I've just gotten there. I've given it so much, it's now starting to boil. But on my graph, it would look like this. I would go up, 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 up until I get to 100 degrees Celsius. And that's where I am now. It's boiling. But let's calculate the number. How much energy did it take to get there? So this is a warming, this is a changing of the temperature, this is a specific heat calculation that we've been working with at the beginning here, and I'm adding to it the latent heat. And so in case you missed this, notice, here's what I'm saying. As you warm up this ice, you have to think about the energy that not only changes the temperature, but also the energy that changes its state. Right? You see, this first calculation was a calculation at saying how much energy did it take to warm up the ice. But the second calculation is also important if you want to know how much energy. Although its temperature didn't go up, you still had to give it that energy. This is the energy to break the bonds. This is the energy to change the state. Now, once I change the state, I have another calculation to do here. This is the calculation that says how much energy is it going to take to warm it up. So if I take the 400 grams and now I multiply by the specific heat of, and this time I will use the 1. Right now it really is water. By the time the bonds have broken, it is now a liquid. And to get it to its boiling point, I need to warm it up from 0 to 100 degrees Celsius. And so if I multiply these together, let's see, 4 times 1 is 4, and then 1, 2, 3, 4 zeros. And so this is saying that it would take 40,000 calories to bring it to a boil. And of course, now, I hope you see the same logic. We're changing states. Now, I'll lift this back up here to hopefully remind you again. What does a gas look like? And so this gas is modeled with this bouncing BB. And so when we warm up this water and we get to this point where we start shaking them and we break the bonds, we're giving it energy that breaks the bonds. It's still